Hi guys, I've got a very naughty little problem for you today. It's a modulus question and it looks extremely difficult, but it becomes very easy if you just have the presence of mind when dealing with modulus functions to express them as piecewise or hybrid functions. And if you do that, it all has a happy ending. So let's have a look at this beast. We've got solving here for x the equation modulus of x minus 4 minus the modulus of x plus 1 equals 5. And we have to work out what values of x that occurs for. Oh goodness gracious. Yes, I know. Doesn't look very easy, but actually it's not so bad. Firstly, we can express each individual modulus term as a piecewise or hybrid function, as I was just saying. And here it comes. So if we let y1 equal the modulus of x minus 4, that would be that. See, it would be that. Now, just as a little aside, it doesn't matter where you put this equals here. You can put the equals bit there on that term, or you can put the equals bit on this term, one or the other, but you just have to include where x is actually equal to 4 in one of those two terms, all right? So that's that one. And secondly, if we let y2 equal minus the modulus of x plus 1, when you sort of do all the machinations and work all that out, it comes to that, okay? Now, it's a lot simpler already, okay? So guys, we've got 4 different functions here. And x is minus 1 and x is 4 are the boundary points, or if you like, boundary lines, where the parts of the piecewise functions change from one piecewise component function to the other, okay? They divide the whole xy Cartesian plane up into like zones, if you like, battle zones, where we're doing battle with these hybrid beasts to work them out. So what we want to do then, once we've got these zones delineated by these boundary lines, we want to add y1 plus y2. In other words, we want to add this thing to this thing, to the minus mod x plus 1 thing, for each zone separated by these boundary lines at x is minus 1 and x is 4. Do you get the deal? It's pretty exciting. So if we do this, ladies and gentlemen, it will enable us to see when y1 plus y2 equals 5, which is what they're asking us for, okay? So it is very useful, I always think, to look at a graph. Look, if you can draw a picture in maths, it's worth 1,000 words and 1,000 headaches. So let's have a look at the graph of y1 plus y2. It's over the screen, so abracadabra, here we go. My goodness, what a disaster at first sight. But it's not so bad when you get right into it. We've got the y-axis here, we've got the x-axis over here, we've got boundary line 1 here where x is 4, and we've got boundary line 2 over here where x is minus 1. Now, this green graph is modulus x minus 4, and to the right of the point where x is 4 it becomes just x minus 4 without the modulus sign. To the left of where x is 4 it becomes the negative of that, so it's y equals minus x plus 4, ladies and gentlemen, okay? Now similarly for this little beastie written in blue here, this was y is minus the modulus of x plus 1, which to the right of where x is minus 1 becomes minus x minus 1, and to the left of the line where x is minus 1 it becomes the negative of that, or y equals x plus 1. Okay, now we've had a good cook's tour of it. Now let's just have a little squiz at this thing and see if we can analyse what we're doing. Now, here are the zones. That's the left-handmost zone. That's everywhere to the left of where x equals minus 1. And I'm going to call that zone 1. Battle zone 1, okay? Now, the objective of the exercise, ladies and gentlemen, is to add up the values of each of these graphs, the blue graph and the green graph, in those respective zones to see what our aggregate value is. For example, if x was minus 2, let's take that value. Now, if you took that specific value of x, according to this rule, y would be minus 2 plus 1, which would be minus 1, wouldn't it? Now, let's go up to the green graph here, which still applies over this dividing line where x is minus 1. The rule for that is y is minus x plus 4 from over here, okay? The graph just continues on its merry way over the dividing line. And For minus x plus 4, if x was minus 2, that would be minus 2 plus 4, which would be plus 2 plus 4, which would get us 6. So, okay, if x is minus 2, this one gets us 6 for the value of the y, this one gets us minus 1 for the value of y, so the aggregate value of y1 plus y2, or in mathematical language, the addition of the ordinates being the y values, we get 5. Well, that's a pretty good result. That's what we were after. So let's do it algebraically now. I'll show you, okay? I'm saying that y1 plus y2 is x plus 1 plus negative x plus 4. Now, if you add that up algebraically, you will get 5. Now, that's absolutely marvellous because this is what we're after. What that's telling us, ladies and gentlemen, is that everywhere in that zone, the combined value of y1 plus y2 is equal to 5. Well, we've hit the jackpot early in the piece. So let's continue on our merry way and look at zone 2 now. In zone 2, we've got a different scenario. We've still got this same green graph, but the blue graph is morphed into this beastie, okay? So it's a different situation. But let's just algebraically add that up now. We've got y1 plus y2 is minus x minus 1 plus the minus x plus 4 we had before over in zone 1 for the green graph. And what does that get us? Minus 2x plus 3. Well, that's a bit different from over here. This does depend on the value of x as to what the aggregate value is. So let's just hold on to that for a minute and we'll go over into zone 3 and see what's going on over there. This is zone 3, which is everywhere to the right of where x equals 4, ladies and gentlemen. Now for zone 3, we know that y1 plus y2 equals, now the situation is different again now because this green graph is morphed into the x minus 4 graph, while the blue graph is still what it was in zone 2, like minus x minus 1. So if you add them all up, what do we get? Oh look, the x's are going to cancel out again, guys. How fascinating. So therefore we're going to get minus 5. So that's telling you that everywhere in this zone the combined value of y1 and y2, that is the added value of y1 plus y2, comes to minus 5. This is very, very interesting. We're reaching the end of the road here, and I think we've got a successful result. So let's go over the screen and analyse what we've found. All right, now, we can see that in zone 1, where x is less than minus 1, that the combined value of y1 and y2 is 5, always, yes? Amazing. So in zone 2, where we had x greater than or equal to minus 1 and less than 4, we can say that the combined value of y1 and y2 is minus 2x plus 3. Well, that depends on the value of x in zone 2. So let's set that equal to 5 and see what comes out of the situation, yeah? We'll solve it for x. Right, so it looks like x is going to be minus 1 only. Well, that's very fascinating. So there is only one value of x in zone 2 as we've described it, and that is when x is minus 1, which is right on the boundary line. So really, zone 3, right up to and including the boundary line with zone 2, has an aggregate value of y1 plus y2 equal to 5. Isn't that great? Right, well let's, in zone 3, where we've got x is greater than 4, we found that the combined value of y1 plus y2 was minus 5, so that's no good to us, is it? So we've done it, guys. We've analysed this thing, and it's really not so awful after all. We found that if we want modulus of x minus 4 minus the modulus of x plus 1 to equal 5, aka y1 plus y2 to equal 5, we know that x has to be less than or equal to minus 1. That's great, isn't it? So there you go. Modulus aren't that bad after all if you express them as piecewise functions. All the best. See you soon.